to tell you, because it's a very nice, a very big power plant. So, my name is Maurice. Welcome, everybody. Welcome, ladies and gentlemen, on this very, very nice power plant, hydroelectric power plant. I say very nice because when you arrive here on this side, you don't see anything. Only the nature. That's very, very nice to see. That was also one of the conditions before we started the construction of this power plant, that the municipality of Koo tell us, you can do what you want, but we won't see anything. All has to be built inside, in a cavern, underground, 40 meters deep. And we are producing here more than 1 unit of a nuclear power plant. So it's very big. I suggest to have this visit in different parts. The first part will be a video during 6-7 minutes, tell you what we see as the energy mix, or the mixed energy, and then a little bit small explanation about how this power plant works. 7 minutes. And then the second step will be going inside, in the cavern, underground, 40 meters deep, to see how it works practically. If you have questions, don't hesitate, you can always interrupt me. Okay? So, can we start?
Yes.
Sorry, I have, I think, 45 or 46 seats. But it's, this video is on, I will have only one here.
One here.
Okay.
Come on, there's one seat here, right?
Yeah.
Not there, there's one seat here. Ah. Just behind. You jump.
What I want to tell you before we see this movie, this video, is the first condition was to protect the nature. That was the first one. The second challenge, that was a very big challenge. The second challenge we have to front is that because we have a very small space inside, underground, all has to be constructed in a very small place, so all has to be constructed vertically. It was a premiere in Europe, that in 1970, to build a system vertically. From all the parts you see in the red color, the running parts have a weight of 850 tons. And that was the second challenge. First challenge is the nature, and to protect the nature, and the second one is to build all vertically. I'll switch off a little bit light here. This one and this one too. That is so. We do it only by the pumping, because by the pumping the pressure is very, very high. Now we'll see the pedals of the turbines completely different, but that's included in the process. So the running takes another running circulation. It's the two moving are different. Pumping is on one side and turbine is on the other side. Here we have around this paddle wheel what we are calling a spiral casing. It's a closed casing. When we with a pelt on the wheel, don't use a closed casing. When we are using a Kaplan system and here a Francis wheel, we need a closed pipe. We call it a spiral casing because the diameter of the entry is bigger than on the outside of the water. So by the pumping, the water is coming in and coming from the center, axial intake, and a radial output of the water. When we are turbining, the intake of the water is radial, and the outside of the water, outlet of the water is axial. So this, on this side we are going to the alternator, and that is what we are seeing now. We are going now inside of the cavern. So,
who manufactured this?
The manufacturer is here. It's Alice Shoulders. is an American company. But the new one is made in combination with Alice Chalmers and CME Cochrane here in Liège. Can we go? Stop. Is managed by Electrovel, and it's only to tell you that we have a direct high voltage lane between Koo and our nuclear power plant in Tihange. And because the two projects has been built together, the first unit in Belgium of the nuclear unit in Tihange, and we had to be ready here before the first megawatt came out, the nuclear power plant. Why? We knew at that time that in the night we produced too much, and you know that the existing in Belgium nuclear power plants, we can modulate it. Always we have to produce the maximum and to work in the maximum power with the maximum power. That, in other words, from 11 o'clock until 6, 7 o'clock we have too much production, and that was also the idea, to use that and to make a reserve of water. So that means that always today we have a direct connection with the nuclear power plant in Tihange, and we are using what they are producing too much by night. So that means that we have 6 units, 3 phases output, 6 times 3 is 18 cables who are going directly to Tihange. Why Koo 1 and why Koo 2? When we started, we didn't have a lot of experience with vertical mounted system, so that we prefer to start with 3 units, and we call it Koo 1, and then later, 8 years later, we built the second series of 3 units, and we call it now Koo 2. But it works exactly the same, the only difference is in the power. So with a little bit experience, we knew that from one unit is roughly 160 megawatts, and we made a step from 160 megawatt with the new one that Koo 2 to 230 total, like you heard it in the video, roughly 1,200 megawatts when all the 6 units are running. So we are going now 20 kV because the machinery works with 20,000 volts, and then when we are producing, the engines produce in voltage 20,000 with a step-up transformer to the high voltage lane under 380 kV. The temperature we can achieve around 45-50 degrees. Of course, all is ventilated, but we don't need any heating system because Mr. Joule gives us a lot of calories, and that is our daily battle to reduce the calories we lose by heating and of the machinery. So that is also to say that all the machineries here are cooled by air, ventilators, and the warm air is by a warm exchanger cooled by the cool water we pump from the lower reservoir in heating exchanger, cool water and warm air. So you see here the 6 units from Koo 1, 1, 2, 3, and then the 4, 5, 6 units of Koo 2. You see it's like in the iceberg, what you see outside this bottom here is roughly 1/7 of the part of the total height. We are going to Koo 2. So, because all of this is installed vertically, under the first and the second cover, we have what we call the the starting motor is an asynchronous starting motor. And an asynchronous starting motor has a torque force very higher than a synchronous motor. Synchronous motor, you don't know in which direction it has to take. Under the first cover is what we call the commutator and the brush system, because what is a running system, if you have to bring some voltage and power on the running part, you can do it with a brush commutator system. And on the top, the blue cover is a tachymeter, is to measure the frequency. For the rotation is here 300 rotations by minute, and always the 50 Hz of the production start from here. A very big cathedral. It's like a cathedral, 110 meter long, 42 meter height, and 25 meter wide. It's a very, very big quantity of rocks. We use that rocks here in the rubbles here. We use it to build the big dam, upside and outside and downside dams. A dam is also very big. What we see a very small part. But here the base of the dams are 50 meters long, wide, and the length of the dams is 130 meters. So it's all what we excavated from and the galleries and from here. I've always used it outside to build the dams. Okay, because I know that some of body are specialized in fluid mechanisms and hydraulica. I told you about the cavitation effect. The cavitation effect is a very, very complicated, complex effect. If you take some books, you can have books of 200 pages telling about what's cavitation. That cavitation is more, as to explain it very shortly, is when you have by a very high speed of water circulation, the water is making vapor. And the vapor, the bubbles of vapor has a very high negative pressure and a high temperature always. And the bubbles of the drops of vapor are going where the pressure is very low, where on the pedal of the wheel, and there they not exploded but imploded, and it's the wave, the dynamic explosion wave, who damage the metal and makes we are not talking about corrosion but about erosion, and therefore we need here some people 1 or 2 times in a year to make some repair. So the second hydraulic effect we have here, more on Koo 2 than on Koo 1, is what we call on the outside of the turbine, we have what we call the draft tube. Of the draft tube. It's also in the form of a cone. So to have a maximum of, to decrease it or in a maximum way the pressure. And in that part we have a form of a cyclone, a whirl, like a whirlpool. And that's the reason why we have 3 in the blue color. We have 2 compressors to inject air and to cut the cyclone, because the cyclone can also damage the inside of the draft tube. So the reason why, and we don't have this effect on the Koo 1, and we have it on Koo 2, and that's the reason why we use compressor with air compressor to cut the cyclone form coming on out the turbine.
Can you explain why it's happening on these 3 turbines and not on the other ones?
Because yes, because the difference is in power output. The principle is the same, but the power and the speed of the water is a little bit lower there for Koo 1. And there's also then the reason that I say that we use it in 88 later. A lot of experience of Koo 1 to improve Koo 2. And with a bigger output, with a bigger electric power output, but also with a bigger flow. The flow is higher here than in Koo 1.
Did you see that in the physical model test that you would have this vortex after the turbine?
We see it we made it this construction has been made in a scale model, and we see that effect in the sky model, in the scale model, so that we knew before we started it that we have to solve the problem of the cyclone. This is one of the ventilators we are using to cool the water and the electric part. Can we walk a little bit faster, please? Because I'm looking through my watch and we have a lot of things to see. So on the top here we have the electric part with the generator. We are walking now just above the paddle wheel we saw outside, and on the water is coming from the radial side, so not in the axial side but on the radial side, and in the casing, in the spiral casing built around here the paddle wheel, we have what we call direction valves, and are moved by this ring. This is what we call the control ring. The control ring is moved by two servo motors. In Brussels, they are saying, I need, for example, 55 megawatts. They position this ring on a certain position. They know roughly how much they have moved the directional valve here, because the direction valves are connected with rods directly on the control ring. So the control ring moves from, let us say, 15 degrees maximum, and this angle is amplified from 0 to 90 degrees with this rods here. That means that we can control the power output from 0 to the maximum of the power output. Here, this unit, the 3 units of Koo 2, by unit is 230 megawatts. This is a full shaft, and it smells a little bit oily. Why? The bearings, all is suspended, the shaft is suspended on a pivot, and the pivot and the upper bearing and the lower bearing here avoid that the shaft can be moved. And we are using here not ball bearings, not cylinder bearings, but oil bearings. So by the starting, oil is going a little bit, raising and lifting a little bit, some couple of millimeters up. Oil is coming in the bearings, and all the system is running on oil bearings. And that's the reason why we have the pipes in brown color and white color are the pipes that are bringing oil in the three upper, the central bearing and the lower bearing, oil bearing. Any questions? Because if you have questions, don't hesitate. It's a full shaft, but it's not a cylinder, but a full shaft. Of course, because the system is controlled and monitoring from Brussels. We are working here only from 8 o'clock until 5 o'clock. Nobody is here after, and nobody in the weekend. Always monitoring from Brussels. Brussels knows also what are the needs on the grid, coming from Elia and coming from other companies who are in charge of the forecasting of the grid power. So that means that we can start it, of course, after an overall, but always controlled from Brussels. The three conditions to move to a switch on the grid is that we have to produce from the generator here the same frequency. We have also to produce the same voltage as on the grid, 20,000 volt with the step-up transformer to 380 kV, because on the high voltage lines we have 380 kV. And the third condition is the phasing. So our phasing has to be in the same phases as on the grid. When the three most important conditions are completed, we automatically close the circuit breaker, and we can produce. We see on this time we don't have any production and don't hear any noises, so that means that we don't produce on this moment. But maybe we have a certain reserve for after 6 o'clock. I don't know exactly the planning, and maybe we have a certain reserve of water in the upper reservoir because we are planned and overall in another power plant. That's a schedule and that planning that I don't know. So we are busy now to change all the PLC from Siemens to Voigt, and it's also a signal that we are doing a lot of new investment in this hydraulic power plant. All the tracks with the PLC are changing, and that goes also a training, special training for our workforce. So we are going now back in the installation that we didn't have until now, because we have a lot of prevalent overhaul. That if we have a big lake in here, all the water will be saved. What we call the laking gallery is a gallery on the bottom of this construction of this engine room, and the water will be pumped with the pump here we call the exhaust pump to the lower reservoir. But until now, after more than 40 years that we are working here, we never had some such laking and overflowing. So it's more preventive work also. We are going now to Koo 1. Oil, the lubrication oil we are using in the bearing is cooled by a heating exchanger. Inside we have small pipes with cool water. It's an exchanger, cool water with oil. So that you can see the difference in with Koo 1 and Koo 2. The principles are exactly the same, but you see that the engine and the elements of parts, the spare parts, are smaller than in the Koo 2. But the principle is exactly the same. Now we are going to see the spheric valve in the level 215. That will be the last part of the visit. And the big are the parts. This is a spherical valve, and you see on the floor it's very dry. The only water we have is some condensation of the warm air with a very cool water and the cool pipes. But I say it again, daily preventive work is to see when we have a small leaking. We were sure that 3 hours later we have a big leaking. So it's we have to be very careful with that. So that is the only valve we have between the upper reservoir and the turbine. On the upper reservoir, 300 meters higher than we have here, so that we have on this point here, if we measure, we have 30 bar. That's also the reason why, for security, we are using the pressure for the closing of this valve with the pressure of the water. We take a part of the water here, 30 bars, to close, and if we have, for example, leaking in all the problems with the electric power supply. So that means that this part also, this pipe has a diameter of 3 meters. So we are with what we call a manifold. A manifold is a collector and a separator. With a manifold, the 8 diameter pipe will be divided in 3 small pipes of 3 meter diameter, bringing water in the turbine. So we are no circulation. When the water is circulated here, we feel a little bit vibration in the pipe. So the pipe is here. So what is a cylinder or a spheric pipe? Is a ball. We call it also a ball valve with a cylinder inside. Now the cylinder is vertically placed against the circulation of the water, and when the cylinder is horizontal in a horizontal position, it has the same diameter than the pipes to avoid the loss of pressure. And also, all the system is not built very fixed on the concrete. We have what we call an expansion system, so that two tubes can move a little bit together. Because if we open here this valve, we have some big changes in the pressure, and to avoid the hammer pressure, and we open it very slowly, and also a compensation and expansion system behind this spherical valve to compensate and to absorb the small or big variation and of the pressure. So here, this valve here, we can open the floor, and we can open the floor on each level, so that we, with a mobile crane in the machine room, we can move on the floor. So you see that the water intake in the turbine is a radial. Takes a radial compensator to the direction of the radial and turn around the pedal. Can move from to the right. It's not possible.
And how many times would you want to have this working to drive? How many? 2, 3?
So the pumping will start at 11 o'clock until tomorrow, 6 o'clock, to empty the low reservoir.
And we're going to be needing all season?
When from 11 o'clock to 6 o'clock.